Welcome back to Unit 6, Geometric Vectors, Lesson 4, Word Problems for Vector Addition. We're going to work through Example 3 and Example 4 of this lesson. Example 1 and 2 are done in the previous video. So we're going to go over a few things here. Bearing is the direction of the resultant vector. The heading is the direction in which the vessel is steered to overcome other forces such as wind or current. Ground velocity. This is the velocity of an object relative to the ground. It is the resultant. Really important. It is the resultant. Or bearing vector when heading, when the heading velocity or the air velocity and the effects of the wind or current are added. So ground velocity is actually the resultant. Now, example 3, I'd just like you please make note of this. These are questions that I love to put on tests. Why? Because there's lots of good concepts going here. Especially there's one keyword here that you will see again and again that I'd like to highlight when we get through this, when we start the problem. So an airplane is flying at an airspeed of 500 kilometers an hour. So there's our magnitude and a heading of 040 degrees. Notice that we're using true bearings rather than quarter bearings. 150 kilometer an hour wind is blowing from, and this is the key word, from a bearing of 120 degrees. From, what does that mean? That means it is going towards the origin. So that means that it is going, the direction is going towards the origin. So direction is going towards the origin. And you'll see why that's important when I draw my geometric vectors. Determine the ground velocity. So again, remember, ground velocity, this means it's just asking me for the resultant of the airplane in the direction of flight. So again, this guy here, this is asking me for the resultant. Alright, so let's draw our vector diagram. So we'll start with the airplane. Here we go. We'll start with the airplane here. It's going in 040 degrees. That looks pretty terrible there. That's 0, 0, 0. That's 0, 90. So I'm going to draw a vector going here. Looks good. We're going here. Alright, so that is right there. That is 500 kilometers per hour. That angle there is 40 degrees. All right. So that is the airplane. That's the airspeed right there. And I'm going to draw another quadrant bearing, or sorry, another true bearings. Mr. Wills, come on. There we go. And again, since this is 40 degrees off this vertical, that's got to be 40 degrees there. That's going to be useful. And here we go. So this is what I like to highlight. 150 kilometers from a bearing of 120 degrees. 120 degrees is between 90 and 180. So I'm going to draw that in. But if you would notice, now 120, so it's about 30, so it's a bit like this. But notice when I draw it, the tip is going towards the origin. So what do I have to do here? I want to put these tip to tail. So I'm going to take this vector and move it over here. And that's the key. From, you're always going to move that vector. So I move it so it goes here. Now I know this is 30 degrees, so I'm going to move that 30 degrees right there. And I know this magnitude, this is 150 kilometers per hour. There we go. So if this is 40, I know this angle here must be 50, which means that this entire angle here must be 80. And then I can also draw my resultant vector. Here's my resultant vector. Starts at the tail of the first, goes to the tip of the second. So there's my resultant right there. All right. So there's my resultant vector. I've got my two magnitudes. I've got my direction. or no, sorry, I've got my angle between the two resultants, so I'm going to use cosine law. So the first thing I want to do is find the magnitude of the ground velocity, which is just my resultant. So I want to find the magnitude, so I'm going to do r squared is equal to 500 squared plus 150 squared. Now if this was 90, I could stop there, but of course it's not, so I've got to use my cosine law. Put that in my calculator. 500 squared plus 150 squared minus 2 times 500 times 100 times 150 times cos of 80. So I get 246,452.8. Square root it. You can see that. So I get 496.4. That'd be kilometers per hour. So that is my ground velocity and my resultant. Now I need the direction. So to get my direction, what I want to do is I want to find this guy here, call that theta. But what I really want is the angle, if I extend this line here, what I really want is this angle here. Let's call that alpha. So I'm going to do, to get the alpha, I'm going to do, once I find my theta, it'll be 40 minus theta, we'll get my alpha. But I have to find theta first because that's inside my triangle, and alpha is unfortunately outside my triangle. So to find my theta, I'm going to use sine law. So sine of theta over 150 is equal to sine of sine of 80 over my r, which is 496.4. If you please excuse me, I'm going to do this quickly so I can see here that my theta is 17.3 degrees. Now I want my alpha. My alpha is actually equal to 40 minus my theta. So alpha is equal to here 22.7 degrees. So now I've got a direction and magnitude. Again, that's going to be north 22.7 degrees east. So therefore, the ground velocity, which is actually just my resultant, is 496.4 kilometers per hour in the direction of north 22.7 degrees east. Alright, last example. A traffic light at an intersection is hanging with two wires of equal length, making an angle 10 degrees below the horizontal. The traffic light weighs 2,500 newtons. What's the tension on each wire? So I need a diagram here. So I'm going to start with my horizontal because it says are hanging with below the horizontal. So here's my horizontal. Pretty terrible horizontal, Mr. Wills, sorry. And then I've got two equal length wires. So I'm going to have, let's say there's my traffic light that's hanging here. So I've got something hanging down 2,500 newtons. And then I've got two vectors here of equal length pulling it up. How do I know it's going this way, Mr. Wills? Because if it was going the other way, those are equal length, by the way. If it was going down, everything, the traffic light would just come crashing down because there's nothing holding it up. And I know these are 10 degrees here. I know that's 10 degrees here. I want to know the tension of the wires. So I'm going to call this T1, T2, so tension 1 and tension 2. But again, I know that the magnitude of T1 is equal to the magnitude of T2 because they are equal length. So I know that fact. All right, how do I do this? I have to arrange this tip to tail. I also know that the sum of the three vectors here is going to be 0. How do I know the sum of the three vectors are 0? Because if it wasn't 0, my traffic light would come crashing down. If these two are too strong, guess what's going to happen then? My traffic light will start going up in the air, which of course is not really realistic. So what do I need to do here? I need to put my three vectors tip to tail. So I'm going to redraw this diagram so that all the vectors are tip to tail. So I'm going to start with this guy here at 2,500 newtons. And then I'm going to bring this guy down here. So there is T1. And I'm going to bring this guy over here. Now, please apologize. I'm going to apologize right now. I had to redraw that one. There we go. So that's T2. Now, here's my horizontal. So I know that's 10 degrees. I also know my horizontal is here, so that's 10 degrees. So I know this is 10 degrees. So now I've got this angle here. I know this angle right here is 20 degrees. All right. Now, if I know those two are 20, I must also know that this angle here, by the way, I know this is 90, of course, vertical, horizontal. So I know this angle here is 80. I know this angle here is 80. So I've got 80, 20, and 80. So I can now find T1 or T2. Doesn't matter which one. So let's find the magnitude of T2. So I've got three angles and one side line, so I need to use sine law. So I'm going to start with magnitude of T2 over sine of 80 is equal to 2,500 over sine of 20. So I know magnitude of T2 is equal to 2,500 sine of 80 over sine of 20. Magnitude of T2 is going to be 7,198.5 newtons. There we go. And that's really all I need to do because I've already got a direction of the vector, so I'm going to write a therefore statement, therefore. Now, Mr. Rolls, what about T1? Well, because they're equal length, I know the tension on both are the same. So therefore, tensions on both wires is 7,198.5 newtons at 10 degrees below the horizontal. So the key to this one here is rearranging this vector tip to tail, because you know that the three vectors here are working in equilibrium. That means if you add those three vectors up, you get the vector of 0. If it wasn't a vector of 0, then either the traffic light would come crashing down or the traffic light start floating up in the air, which of course falling down is a little more realistic than floating up in the air, but that is that.